Hello, this is Mr. Stansbury. I'm going to take you through the 15 C notes on truth tables and equivalence. At the end of this, you should be able to say I can create a truth table. Also that I can determine if compound propositions are logically equivalent, and then also know what a tautology is and what logical contradictions are as well. All right, so let's get into it. Logically equivalent. If you have two compound propositions with identical true-false columns, they are considered to be logically equivalent, and they're also referred to as DeMorgan properties. Okay, so for example 5 from page 503 says show that not P and Q and not P or not Q are logically equivalent. So what we want to do is make a truth table. Okay, so excuse me, this is what a truth table looks like. We have two propositions, P and Q. Okay, so we've got P here and Q here. So we got to come up with all the different possible outcomes of P and Q. So we could have, say, let's start with, say, true and true, or this could be true and false, or this could be false and true, or this could be false and this could be false. Okay, the easiest way to do that is usually what we'll do is we'll start with the last column over and just do true, false, true, false, true, false all the way down the column, and then the next column over true, true, false, false, true, true, false, false, and then if there's any other columns, you go with 4 trues, 4 falses, and you just keep working your way over. And we'll get to that in a few sections. I think it's like 15E or F is when we get to three propositions. Anyway. So we have P and Q. All right, so the first thing we want to do, you really want to just break this down into small, itsy-bitsy pieces. So first thing we want to do is figure out P and Q. So let's do that one right here. So just P and Q. So in order for this to be true, they have to both be true. So true, true, this one is true. P and Q both have to be true, so that's true and false. So then that would therefore make this false. False and true have to both be true, so that's false. And then false, false, that definitely is false because they're both false. All right, next baby step is to do, we've got P and Q. Now we want to do, let's do not P and Q. All right, so that's basically just going to be the opposite of this here. So if P and Q is true, then not P and Q would be false. If that's false, this is true, true, and true, because it's just the opposite of this column here. All right. Now we want to figure out if that's the same as not P and not Q. So let's do not P here. Again, that'll just be the opposite of this column here. So instead of true, true, false, false, we're going to go false, false, true, true, and then not Q will go here. And again, Q is true, false, so that would make this false, true, false, true. Okay, so then this last one here is going to be this whole big idea here. So this is going to be not P or not Q. So again, or just means either one of them have to be true, right? And means they both have to be true, or means either one has to be true. So neither of those are true. So that would be false. One of those is true, so we're true. One of those is true, so we're true, and then both of those are true, so we are true. All right? So we have to then figure out, is this, which is this one here, logically equivalent to this? So let's change colors, make our life a little bit easier. So is this column here the same as this column here? And if you'll notice, false, true, 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 false, true, true, true. So that means that, yes, they are logically equivalent. Yes. Okay, logically equivalent, and again, also called DeMorgan properties. All right, all right. Let us take a short video break, shall we?
So I had to go through the security, obviously, and they have the X-ray area. I don't mind going through it, but I get tired of the businessmen who make way too big a deal out of their computers. You ever hear these people? Excuse me, I have a computer. I have a computer here. I don't know how you're going to handle this, my computer. Oh, is he from the future? They've been around a while, pal. I think they have a way to handle your computation machine. I want to do that with an Etch-a-Sketch, you know? Just do it. See what happens. Excuse me, my laptop. What's that? Didn't see it work? Okay. Want to see the screen change? That's a staircase.
All right, let's move on, shall we? So, example 6 from page 504 says, has us use a DeMorgan property to find the negation of 3 is less than x and x is less than 7. Okay, so what we really want to do then is figure out the opposite of that. So, oops, sorry about that. There we go. So, not 3 is less than x, which is less than 7, is going to be the same thing as x is going to be, instead of be greater than, x is less than 3, and that's going to be less than or equal to, and x is greater than or equal to 7. Okay? So it's basically just the complete opposite of this statement here. Okay? So the original, this one here, if we're going to graph it on a number line, would look like this. We have 3 and 7. It's just less than, not equal to, and x is greater than 3 but less than 7. So it's going to look like this one here. Okay, this here would then also have 3 and 7. Since this one was not filled in, these will be filled in. And then again, since this is pointing together, these are going to point away from each other, right? And that should be the same. X is less than or equal to 3 and greater than or equal to 7. Okay, so that would be the negation. Okay, so this here, and there's the number line equivalency to that. All right, last thing. We have a tautology, which is a compound statement which is true for all possibilities in a truth table. So the entire column has to be true. That's a tautology. A logical contradiction is a compound statement which is false for all possibilities in a truth table. A very simple example of that would be this here. So let's just go through, and P can either be, there's only one thing, so P can either be, let's go back to blue. P can either be true or false, right? So not P is going to be the opposite of that, so it's going to be false or true, right? And then P or not P being true. Again, or you just have to have one of them. So since one of those is true, this will be true. And since one of those is true, this will be true. And then we have P and not P being true. So these both have to be true, and they are not, so that would be false. And then these both have to be true, which they're not, so this is false. Okay, so this one here, since they are both true, this is considered a tautology. Tautology. All right, and then this one here, since they are both false, this is a logical contradiction. Oops, that's supposed to be an R. Logical contradiction. All right. Well, let's see. That's all there is for 15C. So now you should be able to say that I can create a truth table like we've been doing. You can determine if a compound propositions are logically equivalent, like we did on that first example. And then you also know what a tautology is. Everything's true. And then what logical contradictions are. Everything's false in a column. All right. If you have questions, please ask. Thanks.